Good morning. In this video, I'm going to explain how to construct a state table from the transition table. So, in the previous videos, I have explained how to construct transition table and excitation table. So, in this video, I'm going to explain how to construct state table from the uh, transition table. So state table means, see, in the transition table, the states are represented by a binary codes. So if you replace the binary code with the alphanumeric codes, then that is called as state table. For output terminal behavior, binary codes are used to represent the states. So if alphanumeric symbols are used to represent the state, then the resulting table is called as state table. So state table is obtained by replacing binary codes with the alphanumeric codes. Again, it consists of present state section, next state section, and output section. So again, each combination of state variable is assigned to unique to alphanumeric symbol. That means if there are 4 states, so we need to assign 4 unique to alphanumeric symbols. So present state, next state section are obtained. Means in the present state and next state section are obtained by replacing the binary code with the new alphanumeric code assigned. And output section is same. Output section is identical with the output section of transition table. Let's see, this is the transition table of Mealy network. Mealy network. And this is the corresponding state table. See, present state is replaced with the alphanumeric symbol. See, here 00 is replaced with A, and 01 is replaced with B, 10 replaced with C, and 11 is replaced with D. Okay. Similarly, observe next state section when x is equal to 0. So here it is 10. That means 10 is the symbol assigned to 10 is C. So here it is C. Next 11. So that is D. Next again 10. So that is C. So 00 means A. So A. And observe the column when x is equal to 1. Here it is 01. 01 means B. 11 means D. Next 0000, so A. So this is the state table for Mealy network by replacing binary codes with the alphanumeric symbols. Similarly, this is the transition table for Moore network, and this is the corresponding state table. So here also 00 replaced with the A, 01B, 10C, and 11D. So observe the column when xy is equal to 00. So here 00 replaced with the A, 01B, 10C, 11D. And when xy is equal to 01, see it is 10, so means C, 11 means B, 01 means B, 00 means A. And again here 01 means B, 00 A, 00 A, and 10 C. So 11 D, 11 D, 00 A, again 00 A. And here output, some small variation. Here instead of separate column, here we written Z1, Z2, 01, 00, 11, 0. So this is the state table. Next, I'm explaining state diagram. Then what is state diagram? It is a graphical representation of state table. Graphical representation of state table. Okay. So as just we discussed now, state table. So graphical representation of state table is called state diagram. So here in the state diagram, each state is represented by labeled nodes, and transition between the states are indicated by directed branches which are connected to nodes, and outputs are also entered on the state diagram. Okay. So for Mealy sequential network, output appear on the directed branches along with the external inputs. So in that, label for branching for a branch leaving the node consists of present input / output combination for a state associated with the node. Okay, that means on the directed branch we represent both input and output. And for Moore sequential network, output is represented within the nodes, that means included within the nodes along with their associated states. Okay. So let's see state diagram for Mealy network. So here there are 4 states, so it has 4 nodes. It has 4 nodes: A, B, C, D. Okay, na? Now let's see, when present state is A, next state is C. When input is 0 and output is also 0. So that is represented by a directed branch. Let's see the directed branch. See, A to C, input is 0, output is 0. So before the slash is input, after the slash is output. Okay. And when input is 1, next state is B, output is 1. So from A to B, A to B. See the direction A to B. Input is 1, output is 1. Okay. So first row is completed. Come to second row. So present state is B. Next state is D when input is 0 and output is 0. So B to D. See, I draw a line from B to D. When input is 0, output is 0. Also, when input is 1, next state is D and output is 0. So, comma, comma, input is 1, output is 0. That means when the present state is B, next state is D when both input is 0 and 1. Input is 0 and 1. Clear now? Yeah. Now come to present state C. Next state is C when input is 0 and output is 1. So draw a line from C to C. C to C. Okay. Input is 0, output is 1. And when input is 1, it goes to A and output is 0. So C to A. C to A. Input is 0. Sorry, input is 1, output is 0. And next row, present state is D. Okay, next state is A when both input 0 and 1. But when input 0, output is 1, and when input 1, output is 0. So draw a line from D to A. D to A, here represented 0 bar 1, comma 1 bar 0. So this is the state diagram of Mealy network constructed from the state table. Similarly, for Moore network, here small variations. Their outputs are represented on the directed branches. But here outputs are included within the branch, within the node, node. So again here 4 states are there, 4 nodes. 4 nodes. See, A and output is 0, 1. A by 0, 1 and B by 0, 0 and C by 1, 1 and D by 0. So outputs are represented within the nodes. Clear na? Now we'll see directed branches. Present state is A. Next state is A when the input is 0, 0. So A to A. A to A. And in the directed branch, only we represent inputs. Clear na? When it is 0, 1, it is C. So A to C. When it is 1, 0, B. So A to B. A to B when 1, 0. And it goes to D when 1, 1. So A to D when 1, 1. Clear now? Next, second row. It goes to B when 0, 0. So B to B when 0, 0. And it goes to D when 0, 1. B to D and when 0, 1 and 1, 1. 0, 1 and 1, 1. And when it is 1, 0, it goes to A. So B to A when 1, 0. Similarly, third row, C to C when 0, 0. See, C to C when 0, 0. And C to B when 0, 1. C to B when 0, 1. And B to A when 1, 0 and 1, 1. C to A. See, C to A when 1, 0 and 1, 1. And similarly, for present state D to D when 0 0, D to D when 0 0, D to A when 0 1, D to A when 0 1 and 1 1, correct? And D to C when 1 0, D to C when 1 0, when it is 1 0. So this is the state diagram for Moore network. Clear na? So with this analysis procedure is completed. Analysis procedure is complete. So it starts from logic diagram is given. So from the logic diagram we write excitation and output expression, from that transition equation, from that transition table, from transition table to state table, from the state table state diagram. So analysis starts with logic diagram and ends with the state diagram. So these are the small differences between Moore and Mealy model. So here output depends on both present and external inputs, and here depends on only present state. Here there is a chances of occurring false output. False output. Here there is no chances of occurring false output. So here one less number of states are required for the same network, and more number of states are required for the realization of a network. Clear? So these are the analysis procedure. Starts with the logic diagram. We assign state and excitation variables to each flip-flop, and then we wrote excitation and output equation. And to construct a transition table, two ways: either construct excitation table and then transition table, or construct transition equation obtained by applying flip-flop characteristic equations, and then from transition table to state table, state table to state diagram. This is the analysis procedure. And design procedure is exactly opposite. See, first state diagram is given. From the state diagram, state table, the reverse. From the state table, transition table. From the transition table, excitation table. From this, excitation and output expression using K-map, and then at last we write the logic diagram. So design starts with the state diagram, ends with the logic diagram. Analysis starts with the logic diagram and ends with the state diagram. Thank you. So in the next video, I'm going to explain one example which is appeared in the exam. Thank you.